we calculated the electric field inside this sphere that was KQR by R cube 1 by 4 pi epsilon. Right. So inside this sphere, the electric field was going proportional to R. That is the straight line, y equals to mx. Right. And then we were counting the electric field outside of this sphere. So again, we use the Gauss law, right? We counted the Q enclosed, and then we calculated this thing, right? So if we calculate E outside, what would be this thing? So E outside would simply be Q by 4 pi epsilon naught R square. That is behaving like what kind of distribution of charge? What kind of behavior is this thing? Yes. Outside of these, yes.
Is it uniform?
Uniform. So we are considering the charge density to be uniform, right? That is already there. But what I'm talking about is that how this is looking. This is looking something like some, yeah. So there is some resemblance to something. What kind of electric field you get from a particular distribution of charge, or so where have you seen this thing, this relation? If I write that thing, then you guys will understand. Okay, let me write that thing. So this is KQ by R square, right? This thing, right? Right, everyone?
Yes, sir.
So where have you seen this thing? This is very important because this is the most basic thing that you have learned. In the electric field topic, this was the first thing that you learned. Yes, guys. Okay, when do you have this electric field?
If it's at a distance away
Of
from the
a,
center,
yeah, that is what we are.
distance of a charge.
Yeah, absolutely correct. So this is the electric field of a single charge, right? So if we
Yes.
consider a single charge, point charge, so this is a single charge and at a distance r from, right? Then electric field at this P point, that would be simply KQ by R square, right? So
Yes, sir.
if you have a sphere, any distribution, and we are calculating the electric field outside of that sphere, so then it will behave like a point, right? This is what I want to convey, right? Is it clear, guys?
Yes, sir.
Yeah. So E outside is this thing, and we can write that E outside is behaving like 1 over R, right? Because this total charge is a constant thing. Epsilon naught is a constant thing. So this is behaving like 1 over R square. So E outside is 1 over R square. E inside is simply R. So now we can draw the diagram, right? We can draw the figure. So we have this y-axis. On y-axis, we have electric field, right? On x-axis, we have this variable R. And this is the point R equals to capital M. So what is this point? What is this region? Can you guys tell me? What is this region?
Surface.
Surface, right? So that we have seen. So this is the surface, right? R equals to R. So if we are in this region, this is R smaller than R. So this is inside again. Right. If we are in this region, so that is out of the surface, that is the outside bit. Right. So inside at R equals to 0, at center, right? At center, R equals to 0, what would be the electric field?
Maximum.
Maximum. See this relation.
No,
What
no.
would-
Zero.
0, right? So inside at the center, electric field would be 0 because what is the reason? Because of the symmetry, right? So center is the symmetrical center, right? If you calculate the electric field at this rectangular center, this would be 0. If we calculate the electric field at the square center, that would be 0. If we calculate the electric field at the triangle center, that would be 0. Whenever we have a symmetrical center, geometric center, then the electric field forms symmetry because all of the contribution will cancel, right? All the contribution will cancel and you will have net electric field 0. So whenever you have symmetrical center, that is what we call the null point, right? So, which means that if we start from here, electric field is 0, right? So this point. Now it is increasing like R. So what would be the curve or what would be the graph? Proportional to R, y equals to x. So what would be the graph? Right? What is this graph that we have seen? This is a straight line, right? This is a straight line. This C is intercept. So this C tells you that at initial point, where are you? Right? So if C is 0, which means that we are beginning from center. Right? So we are starting from here, right? And then it is increasing. So then this is your graph, straight line, right? At the surface, the electric field is maximum that we have calculated, whatever that was, k cube by r square. And then now it is decreasing as 1 over r square. So this is decreasing as 1 over r square. Right. And then this is increasing as r. And that is your size. So is this graph clear to all of you guys? Is this clear?
Yes, sir.
Okay, then yeah, please note down this part. So we were talking about the outside one. Please note down this thing. And then we'll talk about two things more, right? And then we have the background to study the cavity. Yeah, so please, because the inside one you guys have already noted, so just note down the outside one. So that is why this Gauss law is very, very, very important, right? This has a very nice application. Whenever you have a symmetric kind of thing, so this Gauss law is very handy. Yeah, whenever you guys want me to scroll down the screen, please tell me. Yes, what did you say, Sufyan? Should I move it down, scroll it down?
Yeah.
What about you, Rishta? Note it up to this point.
Yes, sir.
And whenever you guys have completed, please tell.
Done, sir.
Done. Yeah, this is the whenever you have.
Done, sir.
Yeah. Okay, so there is another way to write this. Right, so in any of the places we have not talked about, yeah, so you see that we are only talking about charge. But this charge has what kind of density? This charge has what kind of density? If we are talking about solid sphere. So what kind of density? Yeah, so there was some background noise also, so yeah, so I couldn't hear. What did you say? Sorry, I couldn't hear. So volume, yes, absolutely correct. Right. So we have a volume charge density, which means we have rho. So in terms of rho, how we can write these things, right? In terms of rho. So let us write these things in terms of. So we have so electric field in terms of rho. And remember, we are talking as of now, up to this point, we are only talking about uniform density, right? So up to this point, we are talking about uniform density. I will just write the expression for non-uniform one, but generally you don't have non-uniform one, but that is easy, right? So yeah. So in terms of this one, right, let's write the electric field. So let's say we have this point, inside point, let's say Q, and let's say we have this, right? So I have to use some fainter kind, right? Not this stuff. So we use, sorry. Okay, yeah, so we have this thing, right? And we want to, this is solid, right? This is not hard. If this would have been a hollow sphere, so then we would have a surface charge. But this is solid. Solid and also non-conducting. Because again, if it would have been a conducting sphere, then all the charges would reside on the surface. So again, we have to use the surface area or surface charge density. But this is solid and non-conducting. So we can have 2 points, right? Let's say this is Q point and let's say this is P point. So at Q point inside, we already know that what is the electric field? So electric field is K, what was the answer that we got? So this was, yeah, QR by 4 pi epsilon naught RQ. Right. So QR by 4 pi epsilon naught and R. Right. If we write the vector, so this is going radially outward. Right. So direction would be R. Right, guys? If it is, yeah, at this point we are calculating. So direction, this is R. So direction would be R. Right. Now, we want to relate this charge with the density. So how can we relate? We know that this would be Q by volume. So volume of the sphere is 4 pi by 3 RQ. So I can write 3Q, or let me write only the, right. So let me write that Q would be rho and 4 pi by 3. Right. If you plug this value in here, so this would be rho and 4 pi by 4 pi epsilon naught R cube and 3 and R. So R cube cancels. We have this R and R hat. And this 4 pi cancels, right? So what do we have? We have rho R hat divided by 3 epsilon. Right, so we can write this simply as, so this is going to be very important in the cavity problem. So we will use this rho R vector divided by 3 epsilon. Is it clear, guys?
Yes, sir.
And
Yes,
if we talk about outside, right? If we talk about outside, so what would be that thing? E outside was simply KQ by R square. Right? This R square. And direction is R. Right. So if we talk about this thing, right, and this value is again 1 by 4 pi epsilon naught. This is Q is how much? Rho into 4 pi by 3, and this was RQ. And then we have not this R, right? Because, yeah, so this will be capital, right? This R. And then what we are missing? So this is R. Right, guys? Right. Did we miss anything? So this cancels, this cancels. And this would be rho R cube, right? Divided by 3 epsilon naught and R square, but I have to write this vector. So what I will do is that I will multiply R, I will multiply R and R. Now R and R hat will combine, right? Magnitude and direction. And then this will give me a vector. So this would be rho R cube R vector divided by 3 epsilon naught R. So this would be the electric field outside. Right. Clear, everyone?
Yes, sir.
Okay, so please note down this thing. And now we are ready to talk about that. So please note down this. And then I can directly use this. Right. In terms of, and this is one, right? Yeah, whenever you guys have noted, just take it. So I should write EQ and EP. But yeah, you know these two parts, right? So this is some R and this is some R is varying, right? From inside to outside. So what is this? Whenever you guys have noted, please do. Yeah, you guys have noted, please do.
Um,
Ishita, whenever you are finished,
Yes, sir. Done.
done. Okay, so now let us talk about a problem which is related with cavity, right? So cavity problem, not the dental problem, but the sphere, right? So, and we are only talking about the electric field inside the cavity, right? So outside and then the third region, those are not from the JEE syllabus, they are in advanced syllabus. So in mains, we have only the electric field inside that cavity, right? So let's talk about that. And let me use this. So yeah, this will be useful. So we have a cavity, right? This sphere, and inside this one, we have another. So let me just let's put it in. Right. So this is a cavity, and this is So what you do is that this portion you just take it out, right? So this portion you have taken it out, and the density of this thing is right. So this thing has a density of so, it will take a lot of time. So let me just you just understood that this is filled. Only this part is hollowed out. So it will have let's say if I am talking about there can be three regions, right? One would be inside that cavity, second would be inside this sphere, and third would be the totally outside. So these two regions are not there, only this one is there, right? So let's talk about this region, and we can take any point inside this cavity, right? So let's say that we take this point. Let's say this. So this small sphere will have some center, right? And this bigger sphere will have some center, right? So we are measuring the distance from this part, right? So this is R hat, and this distance is, okay, so this distance is A hat, and we are going from here to here. So let's call it S, right? So these are three set of vectors. And can you guys tell me what would be the triangle's law in this case? What would be the triangle's law? Oh, there is an important call. You guys think about it, and yeah, let me just pick up this. Hello. Yes, guys, there is a parcel that I have picked it. In the moment while we wait for that thing to come, so let me just, yeah. Did you guys figure out what would be the triangles law in here? Very triangles law. You have one vector, this vector, and this vector. So what does triangles law state? This is A, this is S, this is R. So triangles law would be right. Am I correct? Yeah, give me one moment. Somebody is at the door. Give me one. Yes, sorry, guys. I had to do that. Yes, so is it clear one? Is this thing clear, guys?
Yes, sir.
Yes, sir.
Okay, now this thing is clear. So if we talk about this point, we are calculating the electric field at this point, right? So we can imagine this cavity is made up of, or this sphere is made up of two parts, right? The density is rho, right? So we can think about two spheres. One is this bigger one, right, which has this density rho. And then the second one is the smaller one of the size of this cavity, right? And which has the density minus, right? So if we combine those two together, then this part will cancel and it will give zero density. Is this thing clear?
Yes, sir.
So if we talk about these two spheres, so then the contribution would be how many? At this point, electric field contribution would be how many? Let's say that this is A sphere, this is B sphere. Who is texting? Yeah, so what? How many contribution would be there? There are two spheres, so which means there would be two contributions, right? Right? One would be due to this bigger one A, and then second one due to this B. Clear, guys? Is it clear?
Yes, sir.
So if we calculate, the electric field due to this A1, right? What would be EA? And remember, this one is the bigger one, which has energy or this density, charge density rho. And the distance of that point is inside that sphere, outside, or surface. What is the position of that point? Inside the sphere, outside, or at the surface? Think about that and tell me what would be the electric field due to A sphere. Yes, guys, think about it and tell me what would be the electric field. Oh, I have to just. So, what would be the electric field? Right. This position, let me just give you a hint. That is inside. This position is inside that bigger sphere. Right. So, electric field inside in terms of rho, what was that? Yes.
Will it be 0?
Is point at the center.
Okay.
So what is electric field inside of a sphere? If I ask you that you have a sphere and I give you some point, let's say this is center, this distance is r, right? So if I ask you that what is the electric field at this P point, that we have just seen.
That's maximum.
Maximum. What is the electric field inside? 2r by 3 epsilon, right? Clear?
Yes, sir.
So this would be simply rho r by 3 epsilon. Clear, everyone? Now think about you have a smaller sphere, right? You have a smaller sphere, its charge density is minus. From center to this distance is this thing S. So can you guys tell me that what would be the electric field due to the smaller? Yeah. What is the smaller? Okay, let me again ask this question. You have electric field. I want to calculate the electric field inside that sphere whose charge density is minus rho, right? And I'm calculating at this point, right? Inside that point, this distance is S. So what would be the electric field? So that would be minus rho S divided by 3 epsilon naught. Is it correct? Incorrect? Yes. Is it correct or
Yes.
incorrect? Is it this one is correct, right?
Yes, sir.
So we have two contribution, right? Then net electric field, or if I want to write this thing, so this is minus S vector. If I calculate from here the S vector, that would be R minus A. So minus S vector would be A minus R. Is it clear, guys?
Yes, sir.
So I can write this contribution as rho A minus R divided by 3 epsilon, right? So this is EB. Now net electric field due to these two contribution would be the superposition. So if I write this thing, this is rho R by 3 epsilon naught. This is rho A by 3 epsilon naught minus rho R by 3 epsilon. This part will cancel, and E net would simply be rho A by 3 epsilon. Right, so that would be simply the electric field of the cavity. Right, electric field at some point in the cavity is this point. So we have to, we don't have to talk about the distance from the smaller one, the distance from the larger one. We have to just calculate the separation between these 2 points, the separation between the incentives. Right. Is this thing clear, guys?
Yes, sir.
So if we know the separation between the centers of different spheres, we can directly calculate the net electric field. That would be simply rho A by 3 epsilon. Please note it down, and then we will do one question. Right, so one complicated question which will not use this idea, but yeah, but this is important. So electric field inside the cavity, that is important. And this is, yeah, so going to be the second last topic. In the next class, I will start the other chapter, second. Right. Please note it down, and we'll talk about the next. Whenever you guys want me to scroll down this screen, please tell me. Oh, good one.
Done.
Done. What about you, Ishita?
Yes, sir, I'm done.
So then just note down this part and then we'll do one question. So if you can understand that how many contribution are there, then the question becomes easy, right? You think about it. So just think about the contribution and then you can do the research problems.
Done.
Then what about yeah, okay. Yes, Nishita.
Yes,
If
sir,
you
it's done.
done. So yeah, you have a question from the JEE and they ask you, so they are not asking the electric field inside that cavity. So there may be some question depending on that. That will be very quick answer. But there was a very complicated question. The question was that you have this sphere, right, of radius r. This is r. And you have another cavity, right? Something like this one. And this cavity has this radius r by 2. Right. So now you have 2 points. Right. You have this point A and you have this point B. Right. The question is that what would be the mod A divided by mod M? Right. Remember that you have this charge density rho and this will have the charge density minus. Right. So if I calculate the electric field, let's say how many spheres are there? How many spheres are there? Yeah. So 2 spheres are there, right? One with this negative one and then other one with this positive one. So this one we call it, let's say, first sphere and this one as second sphere, right? So if I calculate the electric field at A, so it will have 2 contribution. One would be E1A, second would be E2A. At A point we are calculating, right? Second one would be EV and this one will also have 2 contribution, E1A, EAB, and then E2. Right. So let's individually, let's, how much time do we have? 4 minutes, so we can talk about this question, but yeah, in the next class also we'll discuss this question. But it will have all these will have 2 contributions, right? So if I talk about E1A, right, electric field at A point due to this first sphere. Now you look at this point. So this point is where? Where is this point in context of this first sphere? Where is that one? Where is that point? This point is where in context of this sphere?
Surface.
Surface, right? Absolutely right. So this is at the surface. So if I calculate the electric field, that would be minus rho, right? And whatever is this distance divided by the epsilon. Am I correct with this?
Yes, sir.
So this would be rho r minus and 3 epsilon, 6 epsilon, right? So this is the first contribution, and we are only talking about this A part. Can you tell me, guys, what about the second A? Where is that one? You have that bigger sphere, right? With rho density, I'm talking about that point, A point. Where is that one?
On the surface again.
Surface. I'm talking about the bigger sphere, A point. Bigger sphere, A point.
Oh, center.
Center, right? Absolutely correct. Okay, can you guys tell me which one is the correct spelling? So you have both are correct, right? So
Yeah.
I get, yeah, this one is a British one and this one is the American one, right?
No, something.
It's the opposite way around.
Yeah.
Oh, okay. So yeah. Because lots of the time I just get confused with this. Yeah, so this would be what would be the electric field? I guess people are joining, right? So we have to just leave. So directly 0, right? So if I calculate electric field at a point, that would be E1A plus E2A. That would be simply minus rho r by 6 epsilon. So this
Yes.
is simply EA mod. That would be simply rho r by 6 epsilon, right? So that we have calculated. We will talk about this question in the next class also, right? So yeah, just no need to note it down. I will give you guys some time to note it down, right? So people are waiting. So we have to just leave, right? See you guys. And sorry, I will just make up those 2 classes.